I'm Karen Gask. I work in the big data team at the Office for National Statistics. So I'll be talking through a few examples of where we're starting to use data science at ONS. I'll just do a bit of introduction and setting the scene as to why we're looking at data science in ONS, and then I'll be talking in a bit more depth about a couple of projects. So that's looking at online job vacancy data and also address matching, and then if I've got time I'll just touch on another couple of projects. I'm probably kind of preaching to the converted a bit as to what data science is, but I thought I'd kind of just include this slide for those that don't know. So it's about combining, I guess, two different disciplines historically, so that's computer science and statistics, with a bit of domain knowledge in there. That's quite a kind of famous diagram that's used in data science. But I quite like this, I saw this description of data science on the left-hand side. So it's about applying the best data tools and techniques to a problem. So that's not just numerical data, but increasingly, as Tom said, it's about images and text. And applying kind of newer techniques that have been used in the past, but are now easier because of the amount of kind of computation we've got available now, the amount of kind of computer memory that we've got easily accessible on our computers. So in terms of setting the scene then, so the Better Statistics, Better Decision strategy is the one for UK statistics for 5 years between 2015 and 2020. There are 5 different perspectives which are touched on in this strategy, all of which kind of involve data science, but particularly for us it's the innovative and capable strands that are particularly pertinent to data science at ONS. The strategy also talks about building capability for exploiting richer and more complex data sources, and also keeping pace with advances in technology, which obviously are very pertinent to data science. So this is it's kind of setting the scene for why we're looking at data science in ONS. So going to the first project then, so that's looking at online job vacancies. So currently ONS collects job vacancy data from a survey, but that has quite a lot of limitations, as with any survey. So it is representative. You can choose the definition you have of a job vacancy, because of issues of survey size, getting down to job types and job skills and down to small areas of geography is quite hard by using a survey. So we wondered whether we could use online job vacancy data. So this is obviously job adverts posted onto online job boards to improve or enhance, enrich the survey data, or possibly even replace the survey data. So that was something that we started looking into a couple of years ago. We also wondered whether this type of data might provide us with more timely estimates. So at the moment it takes about 11 weeks from the point, the reference point of the survey to that data being published. And obviously the Bank of England and wants more kind of timely data, wants to understand where the economy is going in kind of real time. Also wondered if using this type of data would reduce the burden for on respondents to respond to the survey, and possibly also make it cheaper. So there are lots of different motivations for looking at this type of data. So we started working with other national statistics institutes in Europe in 2016. We've been looking at it for a couple of years, and there's a second collaborative project starting at the end of this year. As part of that, we've acquired 2 data sets for free. So the first one is from Adzuna, so they've got a job board themselves. So we've got a load of data from them, and also from Burning Glass, so they're a company that web scrapes job vacancies. So they've got quite a lot of data as well. There are quite a lot of challenges with this type of data. So the main one being not all jobs are advertised online. There's quite different coverage if you look at different industries. can be incomplete. Some industries do put a lot of their jobs online, others don't. In the UK, there's no definitive source of online job vacancy data, so some European countries have quite a small number of job portals that people post to. In the UK, it's quite widespread. There are different job boards for different industries, so it's a lot harder, I think, in the UK than in some other European countries. If you've ever looked at some of these job boards, a lot of the data is quite unstructured. And then there's the issue of the definition of a job vacancy in our survey definition, not corresponding to what a job advert is on some of these online boards. So, for example, job adverts might be for vacancies abroad, which we wouldn't be interested in counting. Some job adverts might stay online after the vacancy's filled. There's also this issue of ghost vacancies, which I wasn't aware of before. So this is agencies posting jobs that actually don't exist just to get CVs in from people to add them to their kind of stockpile. So this shows lots of different providers of job vacancy data. So you can see there's quite a variety here. This dotted line is the survey data. So I guess that's what we're trying to mimic. You can see there's a lot of oscillation here. Some of these data sources are for kind of smaller job boards. Some of the data we've accessed, so these two are from kind of European portals. And as I said earlier, we've partnered with these companies to get them to provide our data. But we've also done some web scraping of 7 job portals to access more data. So after all of these issues, what would implementation actually look like? So you can see on the top, you've kind of got from the least feasible option, I suppose, to the most feasible option at the bottom. So it's probably unfeasible to replace the survey with the online job vacancy data. But what might be more feasible would be to now cast the estimates, so we've got a more timely estimate of how many job vacancies there are in the economy. So this is the kind of basic idea of nowcasting. You might have your survey point here, you're waiting for this point here, and you're trying to estimate it by using these variety of data from online job vacancies. So you might be looking to predict what that value is by using something like regression. You might look at bounded regression, trying to calculate what the angle is. Or you might look at classification, so basically have job vacancies gone up or have they gone down? So this is our kind of first attempt at nowcasting. So this is the survey data, and this is where we're trying to kind of nowcast the vacancies. The green dotted line is where we're using the survey alone to do that. And the red dotted line is where we're taking the online job vacancy data and supplementing it. So you can see that by supplementing it, you're actually getting closer to what the survey actually shows. We tried to do this for individual companies, but basically the data is just too sparse at that level. As I said, we kind of looked at different methods, but there are a lot of gaps in the data, and there's quite high oscillation as some companies kind of fall in and fall out of the job boards. So this is illustrated in this graph here. So this is an individual company. The survey data's here, kind of along the top, and then it kind of falls away. This is the online job vacancy data. It's more stable, but obviously much lower. And by using the nowcasting is predicting somewhere up here, but actually because there's no real change in the online job vacancy data, that's why it's kind of predicting it up there. But actually, it's just kind of messy data, and it's just too hard to do for an individual company. So what we found through doing all this work is that agreed access arrangements are generally better than direct web scraping, and that's because websites can change often, so you're often having to change your code to account for these different changes. The data, the online job vacancy data can't replace the survey because there are just too many differences and issues of representativity. The data doesn't correspond to what we're trying to collect. But potentially, could we use this nowcasting idea? It wouldn't be as robust as the survey data, but it might give you an early indication of what's happening in the economy. So we're thinking, how we present these alongside the official estimates. Maybe we could do them as experimental estimates. But obviously, then we'd need to explain to people that these aren't the most robust estimates. So that was one project we looked at. The next project is address matching. This is really important across a lot of different areas in ONS. So we get a lot of different data into ONS, some survey data, some administrative data, as Tom said, increasingly other types of data from companies, and often we need to geo-reference those. We also need to make sure that everyone receives a census form, and when we're going out to collect surveys, we need to make sure that we've got an accurate list of addresses. So addresses are really important for ONS. They're also quite complicated, which makes matching quite hard. I mean, you kind of think of the kind of usual 21 Acacia Avenue, but actually increasingly houses being divided up into flats, and there are kind of annexes. There's quite a lot of change actually in addresses. So what we've done is to develop an address service that matches an input address string to a validated address and to a unique property reference number. So the input address string can kind of be anything. It can be quite messy, unstructured, it might contain typos, it might be quite incomplete. So the user would put these addresses in. Some of the addresses that might get entered in might be quite historic, so some of our use cases are for matching historic data. Other people might want to match to kind of today's point and what addresses look like now. Conversely, we've got some addresses from AddressBase, so this is an Ordnance Survey product. It's a pretty more or less complete and correct list of addresses. It's very structured in terms of kind of building number, building name, street name. There are snapshots at different points in time, so it gets updated every 6 weeks, which is obviously quite often. But organisation and business names aren't always part of the address. So what we've done to try and match these addresses was we realised that control of the input is quite limited. So we need to pass the input string into different tokens, so like building number, building name, street. We could have done that based on rules, so using regular expressions or lookups for town names and counties, for example. But actually, when you start thinking about it, the rules become quite complex quite quickly. And then, this example here of St Paul Street, I just read that as a human as St Paul Street, but obviously as a computer, the ST and the ST obviously look the same to a computer. So what we've done is to look at structured learning. Addresses are semi-structured from kind of smaller units up to larger units. So we've used something called conditional random fields. So that takes the address string and uses features to calculate the likely sequence of words. So you can see this example up here. It's quite a kind of long, complex address. And the algorithm puts it into different categories like sub-building name, street name. The accuracy of the algorithm is about 99% for individual tokens, and the sequence accuracy is about 97%. That was kind of in the early days of training the model. Now it's up to about 98%, and that's on kind of real life addresses after a lot of kind of tweaking that we've done. So then that splits the string into a series of tokens, and then we're more easily able to match it to address space. So we use something called Elasticsearch to do that matching. This provides fast and scalable matching against address space, our kind of gold standard. We need to index the data, but that makes the matching much quicker. And then it calculates the similarity score between that address string and all the addresses in address space. That similarity score isn't necessarily that intuitive, so we've done quite a lot of work recently to calculate a confidence score between 0 and 1 as to how likely we think the match is for a user. So now this service is in public beta, so that means other government departments can request access to it to use it, and as part of that we'd really appreciate some feedback on what users need and any kind of deficiencies people have found in the service. So there's an API available for more technical customers, so they can kind of write code and kind of ping the addresses to us for us to match. There's also a bulk matching service, so that's where you can upload a CSV of addresses and get it matched and then send your CSV back. There's also a web interface for single matches, so you can type in an address here and then it'll come up with a list of likely addresses and a kind of likelihood score there. So the next steps for this project are what we're calling a time machine. So at the moment we're matching to the latest version of address space, but we'd like users, if they want to be able to match against historic addresses. So we're looking at kind of building that service in. We're also extending the services based on a rising customer needs. So more and more users are using the system and giving us feedback about what they want and need from it. So we're responding to that. We work with developers and they're doing a lot of work to scale it up beyond kind of fairly small number of users at the moment. And obviously we're continually looking at improvements in the matching quality and the accuracy of our confidence score. I've got another couple of short examples here of where we've used data science and ONS. So this one is about the crime survey for England and Wales. So people go out and ask the public whether they've been a victim of crime over the past 12 months. And if they have been a victim of crime, they ask for a short description of what happened and then a series of closed questions. Then when that data goes back to the office, there's some manual coding done. So somebody kind of physically looks at these and then classifies the type of crime. And we were wondering whether we could use some machine learning to try and automate some of that coding. So we've used natural language processing on the text that respondents give about what's happened to them, and machine learning on all the closed questions. And we found that about 40% of cases can be automatically matched with an accuracy of over 97%. So they're probably the most common crimes, and they're incidents where only one crime has taken place. We're still going to have to do manual matching in the case of rarer crime types, so things like rapes. And in the case where multiple crimes happen to the same person. So for example, if somebody breaks into your home, assaults you and then steals your car, that's an example of kind of multiple crimes happening and can't easily be kind of sorted out by a model. So people are still going to have to do some manual coding, but we estimate saving about £3,500 a year and freeing up statisticians to spend more time on more complex coding tasks. This is another short example of where we've used data science at ONS. So I said a bit before about how important an accurate address list is. It's also pretty essential for the 2021 census. And we found one of the issues from the last census in 2011 was that caravan homes were recorded inconsistently in different data sets. So sometimes there can be one address for a caravan park, sometimes there's 200, sometimes they're not recorded at all. And census officers spent quite a lot of time trying to establish the facts in the last census about whether people lived there, whether they were holiday homes, that kind of thing. So we obtained some data from the Zoopla website using their application programming interface. We used natural language processing on this property description here, and machine learning to try and identify caravans. The accuracy of the model was above 90%, which I think is probably good enough for our purposes in terms of informing census officers where there might be a caravan park. But it did have difficulty in separating residential properties from holiday home properties, but that was really due to the kind of limited number of labelled examples that we had. This will feed into where to send census officers in 2021, but before we do that, we're going to need to kind of label a lot more cases in order to improve the accuracy of the kind of residential holiday home split for caravans. So I've shown a few kind of examples in the kind of whistle-stop tour of where we're using data science at ONS, so in the job vacancy data analysis and the address matching. So you can see that data science is beginning to be used in our processes and our outputs, but it's not a silver bullet. It's more about evolution and not revolution. Thank you.
My presentation today, the title is Data Science Campus and its project, and I'm going to present it in two sections. So the first section, I'm going to give you a few different projects to give you a flavour of how we apply in a data science campus into various different application domains and what sort of techniques we use, and share our experiences with you. So those go through very quickly, and then on the second part, I'm going to focus on one particular project, which is called Access to Services, that we do it for the Welsh Government, and see how we support them using data science for policy development and so on. So Data Science Campus, as Tom has mentioned that early on, we have we're relatively new in ONS, and the research program, if I look at it from the top level, it can be using data science for three different themes. So the first theme is a better statistic and data. In general, the theme is, can we actually use other sources or alternative data sources to get an earlier indicator for GDP, for example, or some other economic indicator. The other theme is insight and analysis. The insight analysis that we use the Data Science Campus to extracting out some hidden pattern or hidden terminology that maybe we could also use that as a research in the future as a new indicator and understanding the pattern to go forward. And the data science application, we use it for operation and automation. The operation and automation, for example, improving a data science ONS website using NLP, natural language processing technique, to improve on that. So, give a bit more examples in here. The first example is what we call an urban forest project. So this project is about analyzing images to improve data on the local environment. There's estimated £1 billion worth of a tree value, and there are various different tree valuation methods that are associating with social and economic benefits that the tree can provide for the community, for health and well-being, and so on. And air pollution as well. A more notable existing commercial work that's completed by Blue Sky, that's they are on something called a national tree map, already provided, that data set already provided a detailed tree survey. So for this particular project, the project team works with ONS Natural Capital team, and their priority is to really focus on vegetation at the pedestrian level. Pedestrian level as in street level images. So so what techniques do they use? They have used something called a convolution neural network, which is a particular model called PSP-Net. Is pre-trained using other models as well, but the key of it is that they are able to not only to classify vegetation, but also classifying sky and people and building and so on from the street level images. And using that, and on the examples on the right there, bottom right, is that they also done further analysis on that and coupled with a Welsh natural reserves, looking at canopies on the tree size and overlaying on top of the LSOA regions in Cardiff, for example, and coupled with the Welsh index of multiple deprivation index to look at the green space in correlation relationship with a crime rate. So for this project, it has many potential in terms of the green space in relation to social and economic and also environmental impact, etc. And the next one is called Internet Traffic Indicator. So the Internet Traffic Indicator, for this project, we're trying to explore an open source data that is via the Internet Exchange port. And what that is that it has, using the internet volume consumption data, can we extract and understand and provide a new economic indicator? Because in the service sector, we have in the UK, the service sector contribute about 80% of the GDP. So, and the more services of these activities are more reliant on an internet volume. And what the team has done is that scrape the data and plot it at the top by the different regions in Cardiff, in Edinburgh, in Manchester, and in London, for example, by the Internet Exchange point. And what that is that looking at the different gigabit per second and see in terms of the time series. And so they tried, the first thing they did was to look at common pattern around whether these, looking at a certain week or certain month in October to see the weekend. And they see that the weekend, the traffic volume actually dip compared to the weekdays. And also during the weekdays from 5 p.m. onwards to the evening, and there was also a dip there. And similarly, also in Christmas time. So the interesting thing that they find is that by scraping something that is completely open source data, there's actually some pattern that we can, the pattern that we expected from a commercial and social side of the house. And on the left there, they also look at what about some special event? So they look at a World Cup football event on 2006, and the double dip there, as you see, between the kickoff and halftime and the end of match, is that they see that there is a correlation as well. When the people are busy watching the game, they are interacting less with the internet. So it's still initial work completed, but it's quite positive sign that in a research perspective that we can see the correlation between the volume of traffic and also the social aspect and the commercial aspect of it. The third project is identifying emerging technology trends through the pattern application. So the question is, can we actually use patterns to explore terms and extracting terms and emerging and understand emerging technology coming forward? So there are, give you an idea, that there are 90 million global pattern applications being assessed using text analysis. And in order to assess it by human and trying to understand where the patterns are, how the region, where the region is, and also to going forward, where the trends are in technology, it is quite hard. So what this project is trying to achieve is that all of these pattern applications that existed in XML format, they're in various different formats. These are also another challenge. And in something called a worldwide patent database that it's where it's stored. And the team managed through BASE and working with another government department on this exercise as a proof of concept, looked at from 2004 patents to 2016. And they looked at the data of just over 3 million to start off with of patents. And what they've done is that they have added the solution is they try to develop an app, and the application is taking the data. So they're taking the data, looking at the abstract of the patterns in the document and extracting key terms using something called a natural language processing. The natural language processing they have using limitation and also removing the stop word, removing punctuation, and extracting the key term out. And those key terms are then applied something called an algorithm called TF-IDF. To look at the frequency term of these terms in relation to the overall cohort of the overall pattern application documents. So, and they also done some testing and score it, and based on the scoring and extracting out the top end terms automatically to look at the key technology that comes out. So on the bracket there is a term for using the TF-IDF. We're able to extract a term like electric power, power supply, fuel cell, exhaust gas, and so on. So these are completely automated, and they've tested on the 3 million, and they're going to take on the next bigger data set. And initial testing, they use some random testing, about 100 US patents. And what they do is they feed the algorithm and then compare it with the experts, human expert, and then compare, and they got a very good accuracy so far. So that's very interesting work. And the next thing that they are trying to do for this project is that is to look at in a time series whether they would be able to see the trend, looking at something called a RNN, LSTM type of method to see if we can predict the next patent where it's going to be coming. So that's very interesting work in there. And another project here is that understanding the UK port operation and freight behaviour. So in 2016, 484 tons of freight moved through the UK. And in order to support the local authority, there are quite a few issues, or quite a few things that we could help them to understand in order for them to develop the policies in the future. So for example, traffic at the UK port and the capacity utilization, optimization, the inbound, outbound delay of each port, and the big data of the shipping location. So to give you a sense of what they have done, on the right there at the bottom, they've taken two big data in here. One is called the raw AIS and the other one is CRS. So the AIS is automatic identification system. That's about just under 1 terabyte of data, and the CRS is the consolidated European reporting systems. And that's just under 1 gigabyte. And by pulling in those information there into the system that we develop, the AIS system actually is a system that developed in the 1990s. And the ships in here is that all the ships around the port, they all send messages at a frequency when they are underway. It's between 2 to 10 seconds. And when they are anchored at port, they send these AIS messages around every 3 minutes. And what the messages contain a lot of information. It contains the ship identification, it contains the rate of turn, it contains the longitude and latitude, and the status where they are at the moment. So out of that, as you can imagine, by decoding those messages and putting into this what we call a Hadoop distributed file system, which specifically designed to support big data such as this, and then we filter and extracting the data out. And the team initially, because it's a huge amount of data, they've done a lot of visualization. The first visualization, I'm just giving an examples in here. The visualization in terms of just looking at the port activity, when around 25th of December, the port has very little loading activity. And actually, as we go on, and we can see more activities picking up after the Christmas time. And in addition to the visualization, which a lot of projects that we do, we really need to understand the data first. And then after that they've done two areas of work. One is to look at the using clustering, which is called k-mean clustering. And another one that we use is TSNE to reduce the dimensionality of the data in order to segment to do segmentation of the behavior of the shipping going into the port and out of the port. And after they've done that, they also have done further analysis into predicting the delay in the shipping as well. And predicting, they have used assemble learning, which is something called, they use variant assemble learning. XGBoost is the one that they found the most useful, and they managed to get 75% of accuracy within a 2-minute window delay. So these are all very initial research work, and this work can, of course, be expanded onto looking at, can we use this, the freight volume, associating that with early GDP indicator, for example. And then the other one, building on top of the delay model that we just talked about, predicting the delay, we can also look at and support them to understand there are unplanned events, for example, industrial strike action at a particular port. If one port is closed, how would that affect the other port? So again, there's quite a lot of extensions onto that particular work. And this one, another project, is called a synthetic data. Synthetic data, the context of it is that the policymaker would like to get access to a very wide variety of administrative and survey data. But the challenge here is that it's difficult to share the microdata at that level without risking the confidentiality. So what the team has done is that they build a synthetic data generator, which is based on, again, another convolution, another neural networks. And in this one is particular instance is called GAN. For this example in here, just to illustrate the idea of it is that the two neural networks, one network see the actual data, the other never. The generator never see the actual data. So that that protects the privacy and confidentiality. And the generator will actually, through the neural network, to learn. And the result of that is on the right on here, where we have the real data, which show you the blue and the red are in that particular adult census that we just classify into two classifications. One is over 50K, the other group is earning less than 50K, just to give an idea of how this synthetic data can generate the distribution from the real data. So there are 4 variants that they have tried so far, and 4 of them, and they give the one on the far right, which is the WCGAN, and that's actually given the best result, even be able to not only pick out, so from the top to the bottom is the number of what we call an apots, the iteration to learn. The more that it learns, the more that more accuracy. So the bottom there, it shows that it has very, very close distribution to the original data set, even including, unfortunately, resolution is a little small, but even including the outliner as well. So that's a very promising result to start. And another project in here is improving the ONS website. A lot of you probably have used the ONS website. It was a big milestone in 2016 that we launched the new website through many consultations with over 600 individuals from 80 organizations that came up with that, the website. However, there are, as you probably experienced, there are things that we can improve on. And so the team, when they pick this up, they look at what the most challenging one is, how do you capture the user intent? So in this case, what they do is that they use two unsupervised machine learning, something called LDA and Word2Vec. And what they do is that on the left there, the yellow box is they train the Word2Vec using 250, a small corpus of ONS publication. And on the other side, looking at the layman terminology, using the wiki taxonomy, which contain 1.9 billion words in there. And by combining the two, we are able to identify, to help the search engine to understand something that if the terms are very generic, it normally cannot find it. But with this one, even the term is generic, it will still be able to not only find the relevant documentation and also rank the relevancy of it. So the Word2Vec, particularly in this case, again, it's a two-layer neural networks, and it's vectorized the terms that is extracted out from the document. So just to mention the simulation there, it's trying to visualize these the word in 300, this is a 300-dimension vector space using a PCA and TSNU, just for visualization to see the words that how they correlate together. So and actually the tool is these are called TensorBoard. So they are. So the TensorBoard are free and open source. So far I've gone through all the projects, and the access to services is the one that I'm going to go through in a bit more detail, just to give you an idea how we actually solve a project. So I'm not going to use a policy question, but simply just use a simple research question so we can relate to it. How many people in Wales can reach a sport venue with a capacity over 10,000 within 90 minutes using public transport? And the first thing that they did was using the transport data, something called GTFS, and it's also used by Google Map. And the GTFS works very well with open source transport model called a builder called a Open Trip Planner. So the first challenge the team has to do is that not all the data are in GTFS format. Some of them are not, so they have to build converter to build a model. So just to show you the Open Trip Planner as it is, it's quite a primitive in its own right. So the work that we're trying to do is to make that a tool in order to help us to support the Welsh Government to answer some key policy questions. So again, as I said, the formats that they have done the converter for, and then in addition to that, once they have completed the converter, they also build using RShiny to build 3 different functionality on it. One is called point-to-point, isochrome, and coral path. So for the point-to-point is the functionality for that is that, for example, from ONS to Principality Stadium, the tool is able to provide on a particular day and give you an accurate time that is going to travel using a multimodal transport. And this here is that the user can adjust it to just walking it or any multimodal or just train or buses. And the other thing is the coral path. The coral path is, instead of using point-to-point, is using one of the destination point and overlaying the LSOA level, where in this example is in Cardiff, how people living in those LSOA region are accessible to that particular destination. The other one is the isochrone. The isochrone is, if I follow through with the ONS principality, this is looking at the time changes from a particular location. Again, in this case, in the isochrone, is that we're using the isochrone for using that as an origin point and see how many destinations that we can reach within a 90 minutes timescale. Of course, this is parameterized, so we can change it to many that we like. And what we find is that both functionality really tally that answering the question, the simple question from ONS to Principality Stadium is 57 minutes. So how do we then answer the question, how many people for capacity of 10,000 stadiums? So we use the MSOA population weighted centroi, there are 410 of them. And of course, we've got options in terms of using different functions that I've just shown you before. What I'm going to show today, just to use the faster one, so it's a bit easier to see. And from each of the 410 MSOA, this is within 90 minutes. And the 90 minutes that we can see, it's where the key takeaway in here is that the black area where people are residing is unable to get to those stadiums within 90 minutes. So the point is, it's not about stadium. The point is about key services like GP, like key crucial fire services or some other support area. But we use that just to illustrate the idea. And the summary of the result, what that tells us is basically just a figure to show us the majority of MSOA can get to the sports stadium within about 60 minutes, and about 30% of people in overall Wales not able to get to that stadium. So basically, that's, so that really can tell us the population approximately how many based on this centroid. So that's a very flexible tool. And another thing is that we have used 90 minutes for now, or as I said, parameterized, but can we actually go a little bit further in the week and also by hours on a particular weekend? And the answer is yes, we can also do that too. So we can also get a bit more further detail into low granularity by hours to see if we can improve services and bus stop and others. Okay, so summary. The tool is, we believe the tool is, can help multiple area within the Welsh Government, primarily, as I said, the WIM, the Welsh Index Multiple Deprivation, and also the Valley Task Force to help them to plan and analyse where to strategically place the hub to help them to motorise the task force. And then also the South Wales Metro to give them a sensitivity test and introducing new timetable and stops as well. Overall summary, I've covered the data science that we have covered today are highlighted in orange. It's quite a bit of it, but I'm hoping that you find that interesting, and that the variety of application that we use for data science to solve problem is really got a lot of potential. That's my message. Thank you for listening.
It's an honour to have been invited to speak here today. As Tom mentioned, I'm one of the directors of the Data Science Lab at Warwick Business School. Now, in our lab, we're really interested in data from the internet. So data on what people are looking for on Google, data on pictures that people upload to the internet, or data that we gather from games that people play. And one of the key things we wanted to know from this data is whether we can use it to generate measurements of human behaviour that was previously very expensive to measure, very time-consuming to measure, or near impossible to measure. So you can see there's quite a strong overlap between what we do in our lab and the interests around generating useful indicators of human behaviour at national, regional and global scale at the ONS. So given these shared interests, we were delighted to set up a relationship with the Data Science Campus over the past couple of years, which developed from an initial relationship with the big data team. And I'm very happy to have an opportunity to put it on record that the work that the ONS does is genuinely some of the data science research that fills me with the most excitement and respect. And the reason for that is that if you look back through the projects that both the big data team and the data science campus have done, there's a real track record for choosing projects that can be of use across government, for taking a thorough and critical approach to the work that is done, being open with the results, being open with the limitations of what can be done, and also, a real excitement and curiosity about what novel data sources can offer us. So looking at the theme of new data sources in official statistics, I think the two presentations you saw today have highlighted some important general topics. So not only have they shown us some really exciting new work, so for example, around using online data to get quicker estimates of job vacancies, or using data from Google Street View to generate better estimates of how much vegetation we've got. Well, Google Street View is another shared interest. But it's taken a step back and looked at the bigger picture. So I think the title of Jasmine's talk really hit the nail on the head. So Jasmine told us data is coming. And that's really the fundamental reason that there's been a need for a new approach. Historically, both in official statistics and in social science, we'd have a problem we were interested in, and we'd ask, how can we get data to address that problem? Now we're in a world where this data is being left behind, and the question is suddenly, what do we do with this data? And I think the point that Karen made about what data science actually is very strongly related to this. So now we have an issue where we need to try and find what we tend to refer to in our lab as triangles of problems where people really care about the answer, data set that is available, it exists and you've actually got access to it, and a methodology that can truly give you the answer to the problem you cared about using the data that you've got access to. Now, this is not trivial. It's really easy to find one of these things, one problem, one data set, one methodology. It's even fairly straightforward to find two. But if you don't line up all three very carefully, then you're going to very easily end up either wasting your time with a boring project or with a project that simply can't be implemented. So again, these two presentations showed, I think, a whole range of examples where the ONS have succeeded in lining these three things up. So what can we hope to achieve if we do line these three things up? Now, I think there's potentially three opportunities on the horizon. One is to reduce delays in getting measurements about what's going on in the world right now. Another is to reduce cost. And a final goal is to try and measure things we couldn't measure before. So there's something Karen said, it's a set of ambitions that we relate to in academia, in our lab at least, as well. And I think Karen and Jasmine showed a number of ways in which the ONS has made progress towards these goals. So we saw how online data can be used to reduce delays in understanding how many job vacancies are available. We saw some great examples of using online data to measure things we couldn't measure before, for example, the trees example. Now, this question around reducing cost, I think that's more tricky. So as Karen commented, she felt that with the job vacancies approach, there wasn't so much opportunity to save cost by abandoning the original survey and replacing it entirely with the new method. And I think this aligns strongly with what I have seen, at least, across this whole landscape. I've seen very few cases where we've genuinely decided the new approach is so good that we can completely abandon our old data collection approaches. You know, this is true in official statistics, it's true in academia as well. But how we can save cost, as was illustrated today, is to use the new data, the new methodology, perhaps to help inform the data collection. So how do we go about collecting the data? Where should we invest our resources? And to try and improve the efficiency of the processing of the data at the end. Okay, so we've seen we really can use new data, new methodology to generate some new indicators of value. But that still leaves some important questions. Now, one of them Karen touched upon, and that's around communication. So these new estimates that we might come up with, there might be much greater error rates associated with them. But at the same time, they might tell us something that we didn't know before. So for example, with nowcasting, we're generally trying to provide information on what happened a week ago, what happened a month ago, when we might have previously only known what happened a few months ago, or even longer. So to somebody new to the statistics, the nowcasts might look like there's huge errors. You know, they're not as good as the traditional approaches. But if you compare what we know from a nowcast to knowing nothing about what happened a week or a month ago, then clearly we have actually succeeded in reducing uncertainty with these approaches. But how do we communicate that in a useful fashion to potential users of these new indicators? Another question is around what we really need to know about the data and about the methodology. So there's potentially all sorts of issues with this data. Some of them we can make a good guess at. So for example, sampling, we've almost certainly not got a balanced sample with most of these new data sources we're talking about. We're going to have unevenly sampled parts of the country, parts of the population. Other things we might not know, you know, what processing has a company done to this data before they've given it to us? You know, so this is a very different situation to a situation where we've gone out, carefully collected the data ourselves, we know exactly where it's from. With methodology, there's questions as well. So in both of the presentations, we saw, you know, a number of mentions of using neural networks. Now in our lab too, we've seen that the use of neural networks can allow us to do some really exciting things that we couldn't do before. But it can be harder to understand, you know, why has the neural network come to this decision? So it opens the question, what do we need to know about provenance and sampling of data? What do we need to know about the way in which a estimate has been generated if we're going to use those estimates in something as important to all of us as governmental decision making? Are these things a must, or do we need to find an appropriate trade-off with potentially losing valuable opportunities to draw on indicators that we've seen are reliable over careful testing over a prolonged period of time? And finally, I think a challenge that these presentations have shown the ONS can speak well to is of doing this sort of research you know, outside of the kind of environment I live in a university where we know that things might not go right, for example. So there's questions around risk. You know, how can we appropriately invest time in things that might not prove to be useful? There's also questions about skills. What kinds of skills are needed to do this sort of work and to push to push the boundaries of what we understand. But I think actually the ONS has shown with the big data team and with the creation of the data science campus that it's possible to address these questions and to co-locate cutting edge data science research alongside the continuation of delivery of important and long-standing statistics. So those were some of the thoughts that I had about what was presented today. I'm sure you've all got many more, and so look forward to the discussion that will follow.